When you want to start thinking about reaction rates and stuff like that, you can't help but think about the mechanism. Like, why do some chemicals make the reaction go faster? All right. And why is temperature a big deal? Stuff like that. So, in order to figure out the mechanism, which is really how reactants go to products, we need to think about the reaction rate. All right. Like, what makes things go fast and slow. And we also need to think about that concentration dependence. Some chemicals make the reactions go a lot faster if you increase their concentration, but some don't. And the question is, like, why? And that's all stuff we're going to study in this section. Here's an example where it's a compound called cisplatin, all right? And cisplatin is a platinum center. So on the left-hand side here, this kind of silver atom, that's the platinum. And the chlorines there are the kind of gold atoms. And they call it cis, kind of like a cis in a double bond in organic chemistry. In inorganic chemistry, as we'll see in Chem 223, a lot of times cis just means 90 degrees on the central atom. Trans would be 180 degrees across the central metal atom. But anyway, neither here nor there. Cisplatin is somewhat reactive. It'll react with water. One of the chlorides is pushed out, you can see on the product side, and water then bonds to the platinum center. So let's say that we wanted to study this reaction. And this is not something academic. Cisplatin is actually an anti-cancer drug. So maybe we want to figure out the things that make this reaction faster, slower, keep the reactants pure for a longer time. Well, what we'd have to know is we have to study the rate of change of the compound, like how fast is this reaction occurring. So we'd want to know the amount of the cisplatin that's reacting, the moles per liter, divided by the elapsed time. And we'd probably put a negative sign in front of it, of course, because this is a reactant, all that kind of stuff. Let's say that we have a rate for the reaction, which is 4.3 times 10 to the minus 6 molar per second, all right? And what that means is that every second, you're going to use up 4.3 times 10 to the minus 6 moles per liter. Then let's say that we want to know how long it's going to take for a 0.00250 molar solution to react, all right? Well, if you look at those units, you've got a molar per second and a molar. So it shouldn't be too hard to figure out the time for the cisplatin to react. So rate molar per second equals molars, the cisplatin concentration we're starting with, divided by the time elapsed. And in a problem like this, where we want to see about how long it takes, we want to solve for time. So in this problem, you take the concentration you start with and you divide it by the rate, all right? And there's lots of rates, like I saw, and you could see the rates change. But overall, if you want a rough guide as to how long it's going to take, concentration divided by the rate, make sure molar divided by molar cancels out. 1/2 on the bottom becomes second on the top. This reaction is going to take 581 seconds, roughly, to be done, all right? And that's really cool. In my graduate work in graduate school in chemistry, I used to do some reactions that took a long time. But long time meant multiple hours, but how many hours, all right? And when Friday night rolls around, maybe I didn't want to be in the lab looking at my reactants reacting. Maybe I wanted to go to the library and study journals. Actually, what that means is go with my friends on Friday. I love to watch movies, long story. Anyway, so using a process like this, if you have a reaction rate and you know approximately how much of the chemical you're putting in, you can solve for a rough time. And when I did this in my world, I saw it was like 10 hours, all right? So what I would do is go out with my friends to the movies or study journal articles, whatever, for say maybe 8 hours, come back a little bit early because you're never totally sure if you got the right values and stuff. You can then find out what's going on. Now, the rate of the reaction is proportional to the amount of the reactant you start with. So you add more reactant, it's going to take longer, stuff like that, and that seems reasonable. So what you can do then is you can express this as a rate law, all right? And this is kind of an important part. This is the first big topic here we're going to look at in this section. And in a rate law, the rate always equals the rate constant K times the reactant concentration. And there may be something up there in the upper right corner, which we're going to call an order of reaction. We'll talk about that in a little bit. The first thing, though, is that the rate is like finding out what makes a reaction go faster or slower, because the rate, again, is like the speed. And the speed equals rate constant K times the reactants you've got. That little k is going to be important to us. K, the rate constant, is independent of concentration. So you can have as much cisplatinum or as little cisplatinum as you want, not going to affect K. But it does change with temperature. So we'll talk about K in a later lecture a little bit more. But for right now, just realize K is kind of like a holy grail when you want to find out the things that make reactions go faster or slower. If you have the rate constant, you have a lot of power over a given chemical reaction. Let's talk about some generic reactions. Let's take big A, and it's going to react with big B to make X, big X. And little a, little b, and little x, those are stoichiometries, all right? So it could be like 1 magnesium and 2 HCl's making some kind of products, all right? A, B, and X, the little ones, are just the stoichiometry. There's also in this reaction going to be a catalyst C. So what people do sometimes is they'll write a generic rate law, and that's what this line is right here. So we saw in the last slide that rate equals K times, in that case, cisplatinum. Well, for this reaction, we would write rate equals K times the concentration of big A to the M power, and then big B to the N power, and big C to the P power. Now, in the last example, little m was 1, and big A would be that cisplatinum compound. We didn't have B or C, and that's totally fine, but if we did have B and C, we could put them in. We didn't talk about in the last problem about the MNs and Ps, but they are important. Those little exponents are called the reaction orders. We're going to see that some reactants and or catalysts are more important to the speed than others, okay? So the values of M, N, and P are going to be really important to us. In Chem 222 and Chem 223, the reaction orders will be 0, 1, or 2 only. All right, and I'm going to highlight that because that's really important. Reaction orders Mn and P in that generic expression will be 0, 1, or 2 only. All right. After Chem 223, you might see other kinds of orders, and that's fantastic. But in our classes, 0, 1, or 2 only. You have to get the 0, 1, or 2 reaction orders through experiment. There's no way to do it mathematically, all right, and theoretically. You have to sit down in the lab, and I'll show you some examples of that in order to find 0, 1, and 2. For cisplatinum, then, the order was 1. All right, there was like an invisible 1 in the order right there. But you'll see that there's zeros, ones, and sometimes 2s in these reactions, and they can have a big effect on how fast the reaction goes. The overall order for a reaction is the sum of the reaction orders, the individual reaction orders. So if there really are 2 reactants and a catalyst, all affecting the reaction rate, then the overall order would be just M plus N plus P. All right, you add them up. This isn't a super big deal, but it is something you run into once in a while. Most of the time, we're going to be really focused in on trying to find the reaction orders first. And again, those will be zeros, ones, or 2s only. And once you have those, then you can figure out what the rate constant K is. The K is kind of like the holy grail here. If you have a little m, an order of reaction equal to 1, chemists would refer to this as a first order reaction. So if your reaction rate law is rate equals K times A to the first power, we would say that this reaction is first order in A and first order overall, because 1 plus 0, all the rest of them is just 1, no problem. First order is by far the most common kind of order. And if you double the amount of A, you will double the speed of the reaction, because A to the first would be 2 to the first power. Anything to the first power is just itself, so 2 to the 1 is 2. So if A doubles, the rate will double. If A triples, 3 to the first would be 3, then the rate would go up by a factor of 3. On the other hand, if you halve the concentration of A, so you go from like 0.5 molar to 0.25 molar, then it would be like 1/2 to the first power. Your rate would go down by 2. So sometimes if you have a first order reactant and I ran out of chemicals, so I only have half as much, your reaction will actually go half as slow. And we'll talk about that more later. Rate order of 1 is very common. You can have, though, an M value equals to 2, all right? And in this case, we would call a second order reactant. Now, anything to the second power is going to have a different value, a different effect on the rate than the first power was. So let's say that we have a 1 molar A solution, and then we double A to 2 moles per liter. Well, if A has doubled, 2 squared is 4, your rate is going to go up by 4 times. And if you were to triple A, 3 squared is 9, your rate would go up 9 times. Also, if you cut your concentration of A in half, 1/2 squared is 1/4, your speed will go down to 1/4 of what it was. Second order reactants are not as common as first order or zero order. But man, if you have a second order reactant, the reaction will just have crazy speed changes. You'll change things just a little bit, and all of a sudden the rate goes up by so much, or down for that matter. You'll see one if you have one. But another kind of common order for reaction is if you have a 0. Now in math, anything to the 0 power is 1, all right? And there are a lot of examples of 0 order reactants out there. If you double A, and A is a 0 order reactant, 2 to the 0 is just 1. So if your A doubles, there's no effect on the rate. If you have A, 1/2 to 0 is also 1. No effect on the rate. Rate stays the same. You double A, 2 to the 0 is 1. You triple A, 3 to the 0 is 1. Do anything you want to that concentration. It's not going to affect the rate. So you're going to see here 0 order, first order, second order. 0 order and first order are by far more common than second order, but we'll see some second orders too. And all of them have a different effect on how fast the reaction will go, or what the rate of the reaction is.